So I'd like to begin by acknowledging that this is a joint project between Lawrence Berkeley National Laboratory, Lawrence Livermore National Laboratory, and the University of Nevada. It's sponsored by the DOE Exascale Computing program, and I'll have a little more to say about the team and the work as we move along here. Let's see, let me get my pointer teed up. Laser pointer. Okay, I showed this plot earlier in the day, but I wanted to bring it up again because it's very important to the motivation for this project. And what I'm showing you here in this plot is the #1 ranked scientific computer in the world starting in about 1995 and coming up to the present. And I think it's interesting, the last two speakers talked about the DOE Summit computer as well as the new Fugaku computer in Japan. And those are the #1 and #2 ranked computers. Summit held that position till about June, and Japan has taken over with the Fugaku computer. But I think, this points to the healthy competition to really push the state of the art in hardware. And if you look and go through this list, you see that the #1 computer has oscillated between Japan, the US, China, US, Japan. And I really think that's been an extremely healthy competition that has pushed this technology forward. And I guess the other remarkable thing to note, as I mentioned earlier in the day, is that this is continuously up and to the right. There's been almost no pause in the advancement of advanced scientific computing, and that persists. The US Department of Energy has embarked on a major program to build the first exaflop computer. And that computer would reside right up here. And if you want to think about exaflops and get a grip on that, it is a billion floating point operations per second. So these computers are getting so incredibly fast, it's almost hard to grasp the computational capability of these machines. So in the coming year, these two computers are under development. One will be the Aurora computer that'll go at Argonne National Laboratory, and the other will be the Frontier computer, which will be the next computer after Summit at Oak Ridge National Laboratory. And both of those machines are tagged and designed to have beyond exaflop performance, and the hardware is beginning to come in on these right now. So why is that important to this project that we're going to be talking about today? And I'm having trouble advancing my screen. There we go. So DOE they started the Exascale Computing project to be prepared to exploit these hardwares when they came online. And the Exascale Computing project really has two major components. One is called the software technology component, and it is busy building all of the software stack and the computational ecosystem to work on these advanced GPU-based architectures. So that includes, advanced I/O, it includes compilers and all things of that ilk. Then DOE got out in front of these computers by funding some application development projects. And they competitively selected these projects, and they selected 24 in total. And there was a competitive process where people submitted proposals for various scientific applications that demanded this level of computing. Our project that I'm going to talk about, EQSIM, was in fact one of those and was selected. So we are busily preparing since about 2018 to get ready to operate on these machines this fall and in the next year. So what is EQSIM? So EQSIM is a computational framework in our original proposal that's integrated going all the way from fault rupture to structural simulations. And so you can see the cartoon here, ambitious project. And we sold this based on two key issues. #1, if we could develop this technology and it works, we want to do a better job of determining how earthquake ground motions actually vary across a region and how does this impact risk to infrastructure. And if you remember a couple times this morning, we talked about the fact that when you get into the near field of large earthquakes, the data is quite sparse. And so this would really be something, trying to understand the response in the near field that would be a target outcome and application of this project. #2, not to lose sight of the engineering piece, how do complex, and I'll say realistic incident ground motion waveforms actually interact with a particular facility? We talked a little bit this morning about traditionally Engineering practice has grown up around 1D site response calculations and the presumption of vertically propagating shear and compressional waves. Many instances that certainly is not explicitly true. And so one of the other things we want to do in this project is understand that interaction at the interface between the subsurface and the surface. So this is a really, really challenging problem. We talked a little bit about earlier. It's multi-scale for sure. If you're talking about a big earthquake, your Earth model is maybe 100 to 200 kilometers or even larger in terms of extent. We want to model starting from the source through the Earth, and then the waves arriving at a soil and structure site where nonlinearities might occur. And we really want to understand that interaction explicitly. The computational effort to do something like this is proportional to the volume of the model, which is the extent, the earthquake duration, and then it tends to vary as the frequency you've resolved divided by v sub s min, the minimum shear wave velocity, that ratio raised to the 4th power. And so increasing the frequency resolution is really, really tough. And lowering the minimum shear wave velocity and resolving that is really, really tough as well. And that really goes to the heart of the computational challenge. So specifically, every application, EQSIM and all the other applications for the ECP project have to have a well-stated benchmark and goal that they're working towards. So at the very start of this project, we had to define the objectives of this project, and we chose the San Francisco Bay Area as our benchmark model with a computational model domain that looks something about yay big. It's about 120 kilometers by about 80 kilometers. On the right-hand side is what we described as our performance objective. And we're showing here the simulation required for one earthquake realization. In other words, for example, a magnitude 7 Hayward fault rupture event, the computation of that one event. And I'm showing here the wall clock execution time on a fast computer and the frequency that we want to resolve. And historically, prior to the start of this project, the calculations in the Bay Area resided up here. They were resolving maybe 2 hertz and maybe taking 20 to 25 hours on the fastest computer. Well, our pitch and where our objective is to get a 5x increase in frequency. And you remember that frequency scaling, that's very, very difficult to do. And also get about a 5x speed up. And we've talked a lot today about frequency resolution, but we really think getting a 5x speed up and being able to execute these big simulations in maybe 5 hours is incredibly important, because you need to have the scientific throughput and the ability to do a lot of these realizations and explore the parameter space. Well, this is a big jump and a big task. And we knew going in, we were going to have to do a number of things. We were going to have advanced algorithms added to our existing code base. We were going to have to optimize our codes for the hardware, and we were going to need exascale platforms. So we've been working on all of these fronts, getting ready for the arrival of these exascale machines. To our team, this is a really big multidisciplinary problem. So we have to have engineers involved because we're worrying about geotechnical layers and structures. We have to have seismologists involved, and Artie and Arbin. Arbin talked today. Artie will be talking tomorrow about some of the simulations in the Bay Area, so they're critically important. But just as important to this project are the applied mathematicians and the computer scientists that we have to have on board that can really help us advance these technologies and take full exploitation of these advanced supercomputers that are coming online. Additionally, we have some great postdoctoral scholars and graduate students. And honestly, they get to do the fun work on this project because they get to run the codes and actually do the evaluations. So let me tell you what we've been doing. SW4 is a 4th order in space and time summation by parts finite difference code for wave propagation that Anders Peterson and his colleagues built at Lawrence Livermore National Laboratory. We've adopted that as our base compute engine. Don't have time to go through all of our advancements, but we've done a number of things to advance this code. Part of it is the physics. We've advanced the Graves-Pitarka rupture model and adapted it to SW4 and made it automated. We've put in some spatially correlated stochastic geology so we can represent geologic heterogeneities at fine scale. And really important, as I'm going to show you, in just the last 8 months, we have completely revamped the mesh and gridding in SW4. SW4 uses a curvilinear grid in the near surface and a regular Cartesian grid at depth. We have really optimized that through the good work of Anders and his team at Livermore to really have an adaptive grid that is well tailored and optimized to the natural variation of the geologic properties. And that turned out to be an incredibly enabling advancement, as we'll see in a minute. Then, of course, we've been working on workflow. As we do these calculations, anything that slows down or interrupts or is not efficient in your workflow immediately exposes itself when you're doing calculations at 300 billion zones. So we've done a lot of work on the workflow, and we've really been getting ready in terms of our discretizations and distribution of work to operate very efficiently on these GPU-based computers that are going to form the basis of the Exascale platforms that are coming down the pike. This is just an example of some of the simulations. You'll see more tomorrow, but in FY19, we were doing this 10 hertz simulation in the San Francisco Bay Area with about 203 billion grid points at a V sub S min of 500 meters per second. We were using about a quarter of Summit, which is 1,200 nodes, and that took about 19 hours and 52 minutes for a single realization. Remember, we're trying to get to something on the order of 5 hours. FY20, which we completed back in the fall here, we got that down to 63 billion zones in about 6 hours and 58 minutes. So you can see that these algorithm improvements, these very advanced algorithm improvements have really helped, but we've about reached the end of those. I'm showing you here the progress we've made to date. Remember our goal, starting here, wanted to get over here and down to here. Our progress, each one of these letters and blocks here represents a major improvement to the code, either in terms of the algorithms or the optimization. This was working on Cori, which is a 30 petaflop machine at Berkeley Lab. Then we jumped to Summit and did additional work there. And you can see the tremendous boost we got by going up to about a 200 petaflop machine, and what was then the fastest machine in the world, and now is number 2. The grid refinement that I mentioned drove us from here to here. So we're getting awfully close to the promised land here. We're down to about 7 hours. Now, this is at V sub S min equals 500 meters per second. We're currently working on cutting that in half. And we're going to be running our performance assessment this year of V sub S min of 500 meters per second. So overall, good progress. So in the ground motion simulations, we'll know in the next year how far we can go. We're doing a magnitude 7 Hayward fault earthquake right now with a rupture extent that looks about yay big. That's essentially done. We're for all practical purposes there at 5 hours. We're working on this now, lowering our V sub S min to 250 meters per second. We had a number of discussions this morning about why that's important in the San Francisco Bay Area, particularly around the Bay margins. I think we are probably going to get to 5 hours on that on the Exascale machines. And then we're really going to do a stretch goal and try and go up and do a much larger magnitude 7.5 San Andreas event. Can we get there in 5 hours? Maybe in a 5-hour runtime, so we can do those parametric studies. If we drop to V sub S 250, probably can't get there in 5 hours, but we can maybe get to where we can run that. And so the power of these machines that are coming online are incredible, and they're really opening the aperture of the things we can do. I want to very quickly complete this story and talk about our linkage to our engineering codes, particularly since that's a theme of this forum. Our workflow, we've developed 2 mechanisms for linking our structural models to our Earth models. Number 1, we can just do what we call weak coupling, which is simply taking the surface motions from our geophysics model and feeding that directly into our building model in a uniform sense. So that's really, that's really commensurate with the presumption of vertically propagating shear and compression waves, because we're putting that motion uniform across the base. On the other hand, we've also implemented the domain reduction method. And I won't go through that again because a lot of people have talked about that, ET and others today. But the importance of this is it allows you to do soil structure interaction, but it also allows you to represent the full complexity of these complex surface and inclined body waves from the 3D geophysics model and impart those into the engineering model in a way that preserves the complexity of those waves. This took a lot of workflow to really make this efficient. We save an entire surface part of our surface domain. In order to do that, we had to do a very extensive data compression. So we went from terabytes of data with a compression ratio of about 200 and reduced that down to gigabytes of data to be manageable. We can store that on the computer memory. Then we developed a very efficient tool for coupling the 2 codes. And I don't have time to go through the details of that, but we use a spline function interpolation to turn a grid from the SW4 calculation into a continuous displacement field. And that allows us to very easily interpolate to the boundary of the embedded finite element method code, and it can be arbitrarily oriented. So that was a very important development. So this allows us now to do a fully coupled problem. I'm showing you a magnitude 7, representative magnitude 7 earthquake, and we're going to look at the response of this building that's located 2 kilometers off the fault. And you can see that domain reduction boundary really working here as it imparts those complex motions and includes the surface waves and the inclined body waves to shake that structure. We weren't quite so sure how well the domain reduction method was going to work when we had large permanent displacements. Turns out it works just fine. And you can see this displacement, in this case, a fault parallel displacement due to the rupture in the fault offset, the domain reduction had no problem with that at all. So it is really a nice tool to be able to do that coupling. So just a couple of observations. We talked a lot about the fact of the classical idealizations that engineers have had to make to solve these problems. Well, one of the things that we're currently doing with some of our graduate students is really inspecting what do the waveforms, the incident waveforms at the surface look like in the near field. And now that we have this capability, we can begin to look at those waves and look, do they look like inclined body and surface waves, or do they look like vertically propagating waves? Well, I can tell you, and we're going through the details of this now, they don't look like vertically propagating waves in the near field. And so we're doing a comparative study with this new tool between fully 3-dimensional waveforms and site response versus 1D site response to sort of suss that out. You know, we talked a little bit about the complexity of response of buildings in the near field. We're beginning to see that emerge with these calculations. We can literally generate, just like that last model, thousands of stations where we can plop down our building and analyze that building for a given event. And then we can plot what the distribution of risk and damage is. In this case, the maximum peak in a story drift contours. And what we're finding, due to the complexity of the fault rupture process, there's tremendous variability in the response of the building in the near field, as much as a factor of 11, an order of magnitude for buildings that are included within that 10 kilometers of the fault. So this is really allowing us for the first time to expand that database and gain understanding based on thousands of data sets, not a handful of data sets. We're also comparing our results at every turn and every time we can with measured data. And so we compared our building response in this domain, all these gray dots, with building response from the available near field records from Jack Baker's database. You can see there's a real good comparison between the trend and the min and max values there, which gives us some confidence in the model. So those are the kind of interesting parametric studies we can look at. So what's our end game? And I'll end with this slide. Our end game is to make regional scale fault to structure simulations non-heroic. We really want to be able to run a large number of realizations, both to characterize the variability in the fault rupture, as well as to characterize the variability in the geology, so that we can run frequency, high frequency simulations fast, so we can really explore that parameter space and begin to add significantly to the database of synthetic motions. So we are in year 3. We're looking forward to really getting on these new Exascale platforms in the coming year and seeing just how far we can push this on what we hope will be the world's fastest computers about a year from now. So I will end it there.
Okay, great. Thank you.